Good morning, students. Today's topic is Gauss Law. So, Gauss Law states that the total electric flux passing through any closed surface is equal to charge enclosed by that surface divided by epsilon naught. So, the total electric flux is denoted as phi, that is equal to integration E dot ds. So, this is the total electric flux passing through a closed surface, which is equal to charge enclosed by that surface divided by epsilon naught. So epsilon naught, if we bring this to this side, we get epsilon naught into E dot ds is equal to Q enclosed. This is nothing but charge enclosed. We know that the relation between D and E is D is equal to epsilon naught into E. So it is D dot ds is equal to Q enclosed, and this closed surface is nothing but Gaussian surface. So in Gauss law, or according to Gauss law, the Gaussian surface is always a closed surface. Now let me consider one example, that here we have a closed surface in which different charges are distributed. Now we have to find the total flux. And according to the Gauss law, the total flux passing through any closed surface is equal to charge enclosed by that surface. So charge enclosed by this surface is only 3, that is Q1, Q2 and Q3. So phi is equal to Q1 plus Q2 plus Q3, that is total charge enclosed by this surface divided by epsilon naught. Therefore, phi is equal to Q1 plus Q2 plus Q3 by epsilon naught. Similarly, consider another example, that consider a volume in which charge is distributed. And here in this volume, select different differential surfaces. So since charge is distributed, electric field intensity is generated. So the direction of D and E, they are same. Why? Because D and E, they are directly proportional. So the charge is distributed over the volume which contains S. So the total charge enclosed by this volume is given by Q is equal to integration V rho V dV. So inside volume, charge is distributed. So accordingly we get volume charge density. So this is equation 2. So from equation 1 and 2 we get the total charge. So integration closed surface S is equal to D dot ds is equal to rho V dV. This is Maxwell's first equation in integral form. Now we'll apply divergence theorem to this. So what is divergence theorem means? Generally the divergence theorem, it gives the relation between closed surface and volume. So according to the divergence theorem, integration of any vector A, let me consider A is a vector. So integration of any vector A over a closed surface S, this is over a closed surface S, is equal to volume integral of divergence of that vector, this vector, that is A. Divergence means del dot A dV. Now we apply the divergence theorem to the Maxwell's first equation. Means here it is D dot ds, here it is A dot ds. So this D dot ds, here A dot ds has become del dot A dV. So D dot ds become del dot D dV. So by applying divergence theorem, we get del dot D dV is equal to volume integral rho V dV. So all this will get cancelled. So we get del dot D is equal to rho V. So this is Maxwell's first equation in differential form or point form, or this can also be named as Gauss law. Now we'll see some applications of Gauss law. So the applications of Gauss law are, first application is electric field intensity. So electric field intensity due to point charge. Electric field intensity due to point charge. We know that E is equal to E by 4 pi epsilon naught r square into AR, where AR is a unit vector. And according to the Gauss law, we know that integration S E dot ds, that is equal to Q enclosed by epsilon naught. So here we have to find the electric field intensity due to the point charge. So let me consider that which is a point charge. Here we have a point charge Q. Now we have to select the Gaussian surface. So since charge is there, it will generate the electric field intensity. It will generate the electric field. So whenever consider a point charge which is enclosed by a spherical surface. So at any point from Q, electric field intensity is calculated. Means due to this positive charge, the electric field is radially going outward. So in the spherical surface, select any differential surface. Now this direction and this E direction, both of them, they are same. So what does it become? E dot ds cos theta, because here you have E dot ds. So A dot B is equal to AB cos theta. So here we get E ds cos theta, that is equal to Q enclosed by epsilon naught. Since the direction of E and ds, both of them, they are same, we get theta is equal to 0 degrees. So integration cos 0 is 1. So we get E ds is equal to Q enclosed by epsilon naught. So E integration ds is equal to Q by epsilon naught. This is nothing but the area of the spherical surface. So we know the area of the spherical surface because here the Gaussian surface we consider is sphere. So the area of that sphere is 4 pi r square. So E into 4 pi r square is equal to Q by epsilon naught. So E is equal to Q by 4 pi epsilon naught into r square. E is equal to Q by 4 pi epsilon naught r square into AR. If we get this epsilon naught here, we get T. So T is equal to Q by 4 pi r square into AR. So this is the first application. Now second application is we have to find the electric field intensity due to infinite line charge. So this is the infinite line charge. Whenever you have an infinite line and along this some charge is distributed. Now we have to select the appropriate Gaussian surface such that it has to cover this entire length. So the Gaussian surface is a cylinder. So whenever we have a cylinder, it will have a top surface, bottom surface and middle surface. Like for a cylinder, the best example is a water bottle. So in water bottle, we'll be having the top surface, bottom surface and we'll be having two sides. So when the charge is distributed along the cap, top surface in a bottle, we have a cap. So along the cap, the charge is distributed. And even in down also, like in bottom surface also, the charge will be distributed and along sides also the charge will be distributed. Now, wherever the charge is distributed, the electric field intensity is generated. So here and at the sides and even at the bottom, electric field is distributed. Now at the top, if you select any differential surface like this, then that will be going upwards. Means it will be to E and E, it is 90 degrees. Now even down also it will be going downwards. So E direction is this and ds direction is this. So it is 90 degrees. Now here the charge will be moving like this along the sides. So here E and ds directions are same. E and ds directions are same. So here the angle is 90 degrees, means at the top and bottom the angle is 90 degrees and at the side the angle is 0 degrees. So according to the Gauss law, E dot ds, surface integral E dot ds is equal to Q enclosed by epsilon naught. So since here the Gaussian surface is cylinder, the cylindrical surface is divided into three parts: top surface, bottom surface and curved surface. So this integration is divided into three parts into E dot ds is equal to Q enclosed by epsilon naught. So individually if we take top surface, the angle for top surface is 90 degrees. So since cos 90 is 0, cos 90 is 0, we get 0. Even for the bottom surface, cos 90 is 0, so we get 0. But when you go at the sides, E and ds directions, they are same. So when they are same, the angle is 0, so we get EDS. So we get EDS. So E integral ds. So what is here? Since the Gaussian surface is a cylinder, this integral of ds is nothing but we have to take the surface area of the cylinder, that is equal to 2 pi RL. So here what is the charge enclosed? Charge enclosed means for line charge we define the line charge density, that is Q is equal to integral rho L dl. So integration dl is nothing but this complete length. this complete length. So we get rho L into L. That is total length. So rho L into L. So in place of Q, we get rho L into L by epsilon naught. So at left side, we get E into 2 pi RL. L and will get cancelled. So we get E is equal to rho L by 2 pi epsilon naught into R. So in terms of unit vector, it is E is equal to rho L by 2 pi epsilon naught into R into AR, or E is equal to rho L by 2 pi epsilon naught rho into AR. This is if the distance from the z-axis is rho, not R. Okay. Now, electric field intensity due to infinite sheet of charge. So, you have an infinite sheet of charge. Now, here also we took the Gaussian surface as the cylindrical surface. But now the cylindrical surface is placed in this manner. Now, when you see, this is two sides we have. This is front surface, back surface and curved surface. Okay, so according to Gauss law, the condition is E dot ds, surface integral of E dot ds is equal to Q enclosed by epsilon naught. So here we have front surface, back surface and curved surface. So here it will be flowing in this direction. So if we select any differential surface, the direction of E and ds will be same. This here also, if when the charge is distributed, it will be flowing like this. If you select any differential surface, the direction of E and ds will be same. But here, if you select any differential surface, the electric field intensity is going in this direction and the differential surface will be topwards. So it is 90 degrees. So individually, if you do for front surface, both of them they are same. So E dot ds is equal to E ds cos 0. So it is E integral ds. So let me consider that the area of that surface is A. So we can write EA. Similarly, for back surface also E dot ds, that is E ds cos 0. So E integral ds. So it is EA. But here it is 90 degrees. So for curved surface, cos 90 is 0. So this will become 0. So according to the Gauss law, we have front surface plus back surface, that is EA plus EA is equal to, and what is Q means, it is rho s ds, and since ds is also a closed surface like this, ds, like the surface integral of ds is a, means the area of that surface is A. So here also it is A. So it has become rho s A by epsilon naught. So this has become 2EA is equal to rho s A by epsilon naught. A and A will get cancelled. So E is equal to rho s by 2 epsilon naught. So E is equal to rho s by 2 epsilon naught into AN. Okay, fourth application is electric field intensity due to uniformly charged sphere. So here consider a sphere of radius A. Consider a sphere of radius A with uniform charge rho v, because a charge is distributed over the entire sphere, so it is rho v. So to determine D everywhere, we construct a Gaussian surface. One is outside and one is inside. So if it is inside, it is R less than A, and when it is outside, it is R greater than or equal to A separately. So case 1, we consider for R less than or equal to A, the total charge enclosed by the spherical surface of radius R is as shown. So Q enclosed is nothing but volume integral of rho v dv, that is equal to rho v integration v dv. So the volume integral dv is nothing but volume of a dv of a sphere is nothing but r square sine theta dr d theta d phi. So there will be three integrals. We know the limits of r is 0 to r because here the radius, maximum radius is r, and next theta is 0 to pi and phi is 0 to 2 pi. So rho v into phi integration phi is nothing but 0 to 2 pi, and for sine theta d theta it is minus cos theta, and for r square dr it is r cube by 3. If you apply the limit, we get 4 pi r cube by 3 rho v. So according to Gauss law, we know that integration E dot ds is equal to Q enclosed by epsilon naught. So E integration ds is equal to, because E ds cos theta, both directions are same, like E direction and ds directions are same since it is a sphere. For a sphere, both the electric field intensity and the direction of D and E are same. So E integration ds is equal to Q enclosed is 4 pi r cube by 3 epsilon naught into rho v. So E into, this is the area of this sphere, that is 4 pi r square, that is equal to 4 pi r cube by 3 epsilon naught into rho v. So E is equal to, this is r by 3 epsilon naught into rho v. So in terms of unit vector, it is E is equal to r by 3 epsilon naught rho v into ar. And D is equal to r by 3 rho v ar, because epsilon naught, if you get here, we get it is D. So this is for 0 less than r less than or equal to a. Now if you consider, suppose r is greater than a. Now the Gaussian surface is nothing but r is greater than a. So the total limit is, the total radius of the sphere is nothing but it is a. So again Q enclosed is integration volume integral rho v dv. So dv for a sphere is r square sin theta dr d theta d phi. Now rho v, and we know the limits. Limits here are r is 0 to a. Previously it is r is 0 to r. And here it is greater than a, so the maximum limit is a, so it is 0 to a, theta is 0 to pi, and phi is 0 to 2 pi. So if we solve this, we get rho v into 4 pi a cube by 3. So using Gauss law, integration E dot ds is equal to Q enclosed by epsilon naught. So E integration ds is equal to Q enclosed by epsilon naught, because E direction and ds direction, both of them, they are same. So this is equal to E into, this is the area of this sphere. So E into 4 pi r square is equal to rho v into 4 pi a cube by 3 epsilon naught. And E is equal to, therefore, rho v a cube by 3 r square epsilon naught. Therefore, E is equal to rho v a cube by 3 r square epsilon naught into ar, or D is equal to epsilon naught. If we bring here, we get D is equal to rho v a cube by 3 r square into ar. This is for r greater than or equal to a. So this is about Gauss law and few applications of it. Thank you.